row 2 dotted with column 1. So 0, negative 10, plus 2. Negative 8. All right. Row 2, column 2 comes from row 2 dotted with column 2. 0, 20, plus 2, so that's 22. And the 2, 3 entry, row 2, column 3, comes from row 2, column 3. 0, negative 20, plus 0. Oh, and we're done, aren't we? Because I have no more rows of A. So what's the dimensions of this resulting product?
2 by 3.
Uh-huh. Yeah, I didn't need more room. It's just a 2 by 3.
No, 2 by 3.
All right. And so where the dimensions of this comes from, if these match up, I can multiply them, and the dimensions of the product are these guys. 2 by 3. Okay. So a lot of words go into the definition of some of those. You just gotta kind of get the muscle memory of doing it a few times. Okay, so one general observation about this is that the product of A and B, so if A is M by P matrix, and B matches up, so number of columns of A and rows of B, if those match up, this is a P by N, the product of those will be an M by N matrix. Okay, so the result will be those dimensions, N by N. Okay, so any questions so far? Some of you have seen it, some of you haven't, so we don't assume that you've seen all this. Okay. So one result, I think we're not going to do anything. It's all going to be linear algebra here today. Okay, we'll get to that next time. Yeah. All right, so as a result of this, what we saw with multiplication, one thing you can do is you can always multiply two square matrices of the same dimension. And if it's squared, then they just call it order. An order n square matrix is n by n. So let's define a couple of matrices. Say A is 4, 1, negative 2, 6. Same matrix B is 6, 0, 1, negative 5. And let's call this matrix I 1, 0, 0, 1. Okay, just for fun. So what I'd like to do is find the product AB. So multiply the matrices A and B. What are you going to get? What would the dimensions be?
2 by 2.
Right. Row 2, column 1. 12 plus 6. Row 1, column 2. Row 2, column 2. 0, negative minus 30. Okay. All right. Now what I'd like you to do, I'm going to leave you on your own seriously for this one. Multiply B times A. Multiplication is commutative, yeah? So multiply B times A and see if you get the same thing. kind of hard to write them. Rows of B times the columns of A. You gotta cross your hands. It has to be my left hand and my right hand trying to cross them. Or you could rewrite them. People coming up with this?
Oh, 6.
Did I make a mistake?
Yeah, that zero's supposed to be a 6.
Oh, where? With this one?
Yeah.
Row 1, column 2? Row 1, column, oh, 6 plus 0. That's 6, you're right. Pencil.
At least you know that pencil's pretty dark.
Yeah, it's pointing. All right, keeps its point well. All right, so yeah, that's 6 and plus 0, so right, okay. So you're doing like 4 dot products and putting the result in their appropriate entry. Now, are these the same?
No.
Right, this is not the same as A times B. So one thing that we just showed is that matrix multiplication is not commutative. Not the same, okay? Do another calculation here. Find the product of A and that vector I. Row 2, column 1. Row 2. Row 1, column 2. 0. Row 2, column 2. 0 plus 6. What do you notice here? That just equals A. Okay. What happens if you, well, yeah, let's just go ahead and define it. This vector I is special. This is a 2 by 2 identity matrix, order 2 identity matrix. So I is referred to with the ones down the diagonal and 0 on all the other entries. Called the identity matrix. Okay. In this case, the 2 by 2 version. Since, and you can verify that, if I switch the order and multiply I times A, we'd still get A. Okay? There's a number in our real number system that acts a lot like that. So any number times it is the same as it times that number. gives that number back. What number is that in the real? Yeah, the number 1. And we call that the identity element in the real number system. Okay? We have the identity matrix. What would a 3 by 3 identity matrix look like?
1, 0, 1. If it's down the diagonal, it's gonna be 1, 0, 0.
What's that?
If it's just down the one diagonal, it'd be 1, 0, 0.
1, 0, 0.
0, 1,
Say it again.
0. 0, 1, 0.
Right. 0, 1, 0. 0, 0, 1. So we call that the diagonal, the main diagonal. I don't care about this one. This one's the diagonal, going downward from top left to bottom right. 1's on the diagonal, 0's elsewhere. You multiply this by any other 3 by 3 matrix, or have to have rows, columns, 3 columns. That has 3 rows. Yeah. Any m by 3 matrix times this will result in that original matrix. Okay? So it's like the identity element, like the number 1 with multiplication. So we have an identity element. So another thing we can talk about is inverses. We're going to talk about this briefly. And only square matrices can have inverses. An inverse in the real number system, like the number 5, does have an inverse. It's the number I would need to multiply by 5 to equal the identity element, 1. And that number would be 1/5 in the real numbers, right? So some matrices, non-identity matrices, have another matrix that when multiplied, they multiply to give you the identity matrix, okay? Regardless of the order in which they're multiplied. In that case, those matrices are considered inverses of each other. So a square matrix, call it A, has what we call an inverse and it's going to be the same dimensions. If A times B equals B times A, so it's commutative, and either direction I multiply them ends up in that identity matrix. Okay. The notation wise, we refer to the inverse of A as a special name if it's invertible, if it has an inverse. We just like the transpose, we use this superscript, -1, like reciprocal almost, right? Like two numbers, 2/3 and 1/3, they multiply together to give me 1. Sometimes you call that the reciprocal -1, the inverse, multiplicative inverse. Okay. Another thing we saw, determinants. So we've seen determinants of 2 by 2 matrices. All right, somewhat. So we're just going to talk about 2 by 2 and 3 by 3. That's all we got time for. So if A is a 2 by 2 matrix, A, B, C, D, then how do we find its determinant? Right. And they call it one of two ways. Like the absolute value, or in little more wordy, determinant of A. It's like an operation. It takes in a matrix, spits out a value that's the determinant. And if it's a 2 by 2 matrix, it's just the product of the main diagonal minus the product of the other diagonal, AD minus BC. Okay. If the matrix is of a larger dimension, by the way, this is only applies to square matrices. Again, like inverses. Okay. If A is larger, so say A sub 1, 1, A 1, 2, A 1, 3, A 2, 1, A 2, 2, A 2, 3, oops, 3, 1. A3, 2, A3, 3. So if I have a 3 by 3 matrix, now each entry has an invisible sign associated with it. We saw this a little bit talking about the Wronskian, but we assign it invisibly. Each entry has a sign with it, starting at top left corner with a plus, and then alternates. Plus, minus, plus, minus, plus, minus, plus, minus, plus. Right? So we can, what's called, find a determinant by expanding along a row or column. All right, and so this is something you can do along any row or any column. I'll just do it across the first row. Okay, so this one is a positive. Starting there, it's A11 times a special determinant if I cross out the first column and first row. So the row and column in which that entry appears, we have a 2 by 2. So that first entry times the determinant of that smaller matrix. A22, A23, A32, A sub 3, 3. Okay? Minus, or plus, my negative 1, minus, and if I expand it along the first row, A sub 1, 2, times the matrix where that row and that column is deleted, A2, 1, A2, 3, A3, 1, A3, 3. Finally, plus, and then the last one in the row, A1, 3. And when we delete row and column that appears in, I got A2, 1, A2, 2, A3, 1, A3, 2. So that's expanding it along there. And it's higher degree ones are defined recursively. Okay, so if I know how to find the determinant of a 2 by 2, then the matrix, or the determinant of the 3 by 3 is defined recursively. So the determinant of a 3 by 3 is defined in terms of a matrix of a 2 by 2. If I know how to do that, then I can find the determinant of that larger one. You don't want to do it by hand for a 4 by 4 larger. Yeah.
Can we use other methods?
Yeah, like a calculator, or putting it into, yeah, there's all sorts of things, upper triangular form, multiplying the, anyway. Yes, there are other ways. Oh, say for a second, I just want to hit one more thing. Say we have a vector or something, a column vector of unknowns, say x1, x2. And my A is as before, oops, as the previous page. Say A is 4, 1, negative 2, 6. Multiply A and X. I always like to see them arranged in that other way, but what would that look like? Right, rows of A times columns of that, so 4x, 4x1 plus x2, right? And the second row, and there's only one column, so second row, first column would be negative 2x1 plus 6x2. All right. So we'll start to be doing stuff like this where we have a column vector of unknowns, dependent variables or something, okay? And writing things in that form, okay? Matrix multiples. All right, for now, we're gonna have to call it quits. I want to get this out to you as far as, this is just practice 5.1 supplementary thing that you guys can work on, some matrix work. Good practice. All right, but I also got the projects. So we're gonna get that out to you. And it's pretty straightforward, so it's not like you're going to be doing research, you know, and give me a bibliography that's 3 pages long or anything like that. So here it is. The project is just going to consist of 2 problems. Now they do have some multiple parts, okay, but they're fairly straightforward and computational. And the good news is that you can pretty much do them with the knowledge that you have now. So it's not something that you're going to learn end of week 9 that you have to wait for to learn until you can finish it.
Is this group or individual?
So you may work with people, you know, however, I mean, if you want to do that, you can consult with each other, work together, but everybody has to do their own write-up. And the thing about that write-up, oh gosh, I did not have the point on here, we'll talk about that next time. The write-up needs to be done on some sort of word processor, so if you use LaTeX, great. If you want to use Word or something like that, that's fine as well. But it does have to be done on a word processor, okay? Including any tables that you create, any graphs. There is one where you do have to include a graph. So you can do this using whatever, WinPlot, Maple can handle it all easily, Maple, WinPlot, even Graph. Free software, Graph, you can plot a function of one variable. And you can capture that, you can just save the image and import it into a Word document you can use in Word. Same thing with Maple. Right click, you can save it if you want, import it into your document. Control C, put it in there.
Wednesday.
What's that?
Thursday 6-5.
Thursday 6-5. I get mixed up between my Monday, Wednesday classes and my Tuesday, Thursday classes. So this is
Thursday
Thursday
7-4.
7-4. We're not here July.
Let's make it June, July anyway.
Yeah, I'm okay with that.
Yeah, after rates are out.
So that's the last day of class in the 10th week before finals week.
So
Okay.
all that's involved in it is just a nice, pretty formal write-up?
There's a formal write. You got to do the work.
Oh, yeah. No, like PowerPoints or something?
No, there's not going to be any in class. We're not talking to in class presentation. It's not going to be presentation. So for next time, another thing to put on the on your radar is the fact that we have an exam
Next Thursday.
next Thursday. And that's a 1 week from this Thursday. So for this Thursday, we do have a problem set due, but section 4.1 homework. Where am I? Here we go. Jeez. Holy jeez. All right. So for Thursday, section 4.1 homework. I'd like you to go ahead and read. It's a big read, but you know, pace it out. Section 5.1 plus. This is for your own benefit. Finish that activity 5.1. Work on that activity. Have matrix stuff and practice. Okay. And we do have a problem set due. Okay. All right. We'll continue with 5.1 next time. Oh. And I got stuff to pass out too. Well, I got the quizzes. Nicholas.
What'd you get for the last one?
Very.
Was it Phil's or what is this?